Yeah, good. Okay, hello everybody. Let's get started. There's lots of awesome to talk about, so let's get going. Hello, my name's James Strachan. I'm hopefully going to talk about lots of interesting open source stuff that you can all play with as soon as you get home, or right now if you get bored in my talk. I'm going to start off, I'm going to talk about quite a lot of different open source bits and bobs. Before I start, I want to step back a little bit and just talk a little bit about how we're all trying to go faster. Now, the IT industry goes through various trends. There was object orientation used to be a big thing, and a focus on reuse, and then it was all about services and SOA. Now there's a current thing of how do we go faster? How do we deliver value to our customers quicker? Now, at first you might think, well, does it really matter if it takes me 1 week or 2 weeks to deliver some value? The aim isn't really, the point isn't really the amount of time it takes, it's how many iterations can you get in, right? Software is really kind of complicated. As geeks, we can often get sidetracked in how caching works in a persistence ORM layer and kind of forget what is it that the user actually wants, what is the value we should be aiming for. So trying to deliver value to customers faster should be our kind of aim, right? It's how do we do that as quick as we can? And then once we've delivered some value, how do we then iterate to go quicker and quicker and quicker? Because it's the iterations that make an awesome product. The first product's always crap, right? It's a bit rubbish. It's the 5th, 6th, 7th, 10th generation that's the better one. So the quicker we can deliver value, the quicker we can iterate, find out what the customer really wants, right? Pretty much every system I've ever seen where there's specifications written and design documents or whatever, the first version that comes out, customers see it and go, oh, I didn't mean that. I meant something totally different. So you need to iterate a lot, right? The idea of working in an ivory tower for 2 years and then going, da-da, is kind of, you're doomed to failure there. So how do we go quick? How do we go fast? So there's two kind of buzzwords right now. You've probably heard these before, DevOps and microservices. They're kind of related. They're kind of different sides of the same coin. It's really about how do we deliver software faster. Now, to deliver software and value faster, it's actually more complicated. It's harder, right? So it's more complicated, but you can go faster with this extra complexity. So one way of doing it is refactoring software, so a purely technical thing. Take your big hunk of monolith code and split it into lots of separate pieces. Now you probably kind of do this already and you think, well, everyone does that, don't they? The big difference though is those separate pieces are then released separately. So each microservice has its own life cycle, right? You release each microservice when it needs to be released. The internet is kind of like a microservice system you could think of, right? There isn't one release. We don't go, the internet's down today while 2.0 goes out, and you roll out the whole thing, right? There's lots of little microservices that are being rolled out all the time. It's much more complicated, it's much more harder, but it means you can move faster, right? So one of it is splitting your system into lots of little tiny little pieces that all iterate independently. Some systems get stable and then just have the odd bug fix. Other systems iterate quickly as you deliver more and more value. The bigger change with microservices and DevOps, which is the real hard one, is actually human and organizational. You split your one big team into lots of small teams working on separate things, so separate independent teams. If you've ever read the Mythical Man Month book, it's a very old book and it talks about you have a big project and it's going too slow. If you add more people to it, it goes slower, right? Which might seem counterintuitive at first, but the more people in a team, the slower it tends to go because of talking and meetings and the kind of the chit-chat. So if you want to go faster, take one team, refactor it into 10 teams, assuming you've got lots of people. Okay, if you've only got 10 people or one person, that wouldn't really work. But assuming you've got quite a lot of people, split them into small teams, making small things independently, and this is the key point, independently, minimize the coordination between teams, and you can all go much quicker. Now, the other thing that's a big change with particularly the DevOps movement is, and the cloud as well, we used to have silos. Some of you probably still may do have silos. We have lots at Red Hat, unfortunately, which is slightly embarrassing, but let's not talk about that right now. Silos are really bad. You might have a development silo, and then a testing silo, and then a support silo, and then an operations silo. And maybe a design silo and an analyst silo. And you have people doing one function and chucking things over the wall. So the spec guy will write a spec and chuck it away. And then the coder will then try code it and then chuck it over the wall. And then the tester will go, oh my God, this doesn't even work. And what does the user want anyways? And having these silos means you have lots of time. It takes a lot of time to move things between the silos. One of the big things of the DevOps movement is by having one team with testers and designers and coders and operations people in one team working on one thing together, so it's one flat team. It minimizes that silo and makes it quicker to take some code, put it in development, put it in testing, put it in production, and iterate quickly, right? The less silos we have, the quicker we can move, and the more we develop software that's fit for production. The further a developer is away from production, the less likely that developer is to write code that runs well in production, right? So the more that one team is looking after the whole spectrum of a piece of software, the more you write software that's more easily testable, easily monitorable, easily manageable, right? So it's almost like from day one, you should write some code and go straight to production, and then get used to rolling upgrades to production, because then you start thinking about making your software easy to upgrade, easy to manage and monitor. Okay. The other big thing about DevOps is automate the crap out of everything, right? Because as soon as you start having 10 microservices, and each one of those is doing a release every, say, day, you're doing 10 releases a day. That's quite a lot of releases, right? And if you've got, say, 4 machines, you don't want to be SSHing into a machine and with Vi editing things and curling things on the command line and crap like that, right? Everything needs to be automated. Every build needs to be automated. Every release needs to be automated. Every rolling upgrade should be automated. So the more you do of something, the more you should be automating it, so then you can get better at it, right? A lot of DevOps people talk about if something's painful, do it more often, because then you figure out a way of making it less painful, right? So you should release often and automate everything. Okay, so that's the general basis of all this microservices and DevOps thing. So that all sounds kind of cool, but then how the hell do you do any of this stuff, right? How do you release something 10 times a day, and how do you have 10 different things that are running independently, and how do you keep track of all this kind of stuff? So what we kind of need is a platform for developing microservices on top of, where we can have lots of different teams writing lots of different microservices. We can all kind of work together, and we can all move software quickly through development, testing, staging, and production, right? So we need things like continuous integration and continuous delivery, where we're automating the builds of things and the migration of those pieces of software through the platform. Okay, so let me tell you about the implementation details for how you can do this right now. Professor Dave mentioned Docker briefly. Docker has changed everything, really. I'm kind of old, not quite as old as Dave, but I'm kind of almost that old. I've been writing software for a long time. Docker changes everything, really. So in the Java world, we've got into the habit of making like a jar file or a WAR file and moving that from development to test to production, which is a good thing, right? We make a binary. You're not meant to unpack it. You're not meant to hack it and then zip it back up again. You're meant to just take that binary and move that binary through the environments, and that's good. That's good. The only slight problem is the application servers and the configuration and the JVM and the operating system and all that kind of stuff is not in the binary. The binary is just some Java stuff, right? So that WAR might work perfectly on your Windows laptop using the version of Tomcat you lovingly installed 2 years ago, but it might not work on the Linux operating system that's in the production environment that some other guy installed some other JVM and some other operating system, and yada, yada. You get the picture, right? So you're not really testing the operating system and the JVM and the application server. There's so much that can go wrong by taking that WAR and moving it to production, right? Because you're not really testing everything. You're just testing the WAR, and you're assuming the WAR is in an app server that's tested, that's configured just so everything kind of works. What Docker does is change everything, in that you can put everything you need in a container. So the JVM, the operating system patches, any shared libraries you need, any binaries, any environment variables, whatever version of the app server you wish to use, Tomcat, Jetty, Carafe, Wildfly, whatever, the exact configuration of JNDI for the WAR and all this kind of crap, right? So Docker really changes everything. For me, the biggest thing about Docker is the metaphor, the shipping container. Shipping containers totally revolutionized the transportation industry. In the old days, people would just transport, barrels and bags and sacks and random stuff. Then somebody came up with the idea of a standard shipping container, which meant forklift trucks knew how to pick up a shipping container. You could get cranes and tractors and trailers and ships could stack them vertically, horizontally, and the door was always in the same place. You could have standard tools for getting things in and out. And you knew if you have multiple shipping containers next to each other, they're not going to interfere with each other, right? One's not going to give off a gas and the other's going to leak liquid, and all the explosions are going to happen and stuff like that. So Docker is the same kind of thing for software. It's a standard way of putting something in a box, in a virtual container, and then it can just be installed and run on any machine, right? If ever you've tried to install Oracle, say, or even most databases, to be fair, if ever you try to install NPM or GEMS or whatever, oh, damn, I previously installed a slightly different version of something that conflicts with the thing I'm trying to install right now. Oh, let me trash my entire hard drive and start again. Installing software is a pain in the ass, right? If you configure stuff in a Docker container, anybody can just run it, right, in just one command, which I'll show you in a minute. So Docker has changed everything in terms of packaging software. What actually happens under the covers is it's still just a Linux process. All a Docker container really is it's using Linux containers, things like C groups and namespaces and that kind of stuff, so that all you're doing is running one process. It's still just one Linux operating system process. The process kind of thinks it's like it's in a VM. So it looks and feels like each process has its own VM, but really each process is just isolated from the other processes. So with virtualization is kind of cool, but it's kind of sad these days. Every time you make a VM, you have to run a whole new operating system that's pretending to be a whole new computer, right? With Docker containers, you're just running a process in a container so that you're sharing the operating system, right? You don't need to run lots and lots of Linux kernels. You don't need to run lots and lots of device drivers pretending to be a file system or memory or the keyboard or God knows what else, right? So a Docker container is just a process, but it's just isolated. So each process gets their own disk, so you don't have processes clobbering each other's file systems by accident. You know, both two programs might use /temp/foo, right? That's fine in Docker because they're isolated. Each container also gets its own ports. If ever you've tried and run Tomcat twice on a laptop, you have to open up the config files and search and replace all those ports because there's only one port 8080 on your laptop, right? In Docker, every container can say, I'm going to listen on port 8080, and that's cool. And every container does because every container gets its own networking stack, so it can listen on whatever ports it wants. The slightly complicated thing is if you're on your laptop and you want to talk to those two Tomcats, each one externally gets its own different port because internally Docker's doing port swizzling from the outside in, but don't worry about that. So basically the idea behind Docker is put your stuff in a box, in a container, and then anybody can run it on any computer, plus you can densely pack these containers together onto hardware. Studies have said it's kind of 20%-ish hardware for free if you switch from virtualization to containers, because you're not running 20, you can run 20 processes on a box without 20 Linux operating systems on the box, right? You're just running 20 processes. There's other stuff Docker can do as well, by the way. You can have runaway processes that get into a CPU loop. That one bad process can take up 100% of your CPU, and it can starve, whether it's CPU or I/O or disk or network, it can starve all of the other containers. Docker lets you set limits. You can say this container can only use 10% of the CPU. Docker kind of turns a Linux box into a bit like the old mainframes, where you could totally slice the box up into pieces, allocate those to different programs, and you kind of have your own little mini supercomputer or mainframe. So Docker is awesome, it changes everything. This is how you run it. Like if you learn one command today, try make it this, then you can run pretty much every software that anybody's ever made that runs on Linux. Docker run, and then space, then a couple of command line flags depending on if you want an interactive terminal and what you want to do with the port mappings, don't worry about that detail. And then the last bit is the name of the Docker image, and that's it. And that name of the Docker image could be Postgres, it could be Memcached, it could be a Ruby on Rails app, it could be Erlang, it could be a Java app, a Node.js app, a Swift app, it could be anything, right? You don't have to figure out how to do gem install or npm this or that, or any kind of package manager or yum update or RPMs. You just do Docker run and you're good to go. So it's nice and simple. So Docker changes everything in terms of delivering software, right? It's a thing of awesome. And if you're delivering software to run on Linux, please use Docker containers. It will save you loads and loads of trouble. And the people running your software will thank you for it. Okay, so that's Docker. The thing about Docker, though, is it's kind of like running a program on the command line. You type docker run blah, 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 and then something will run for a while, and then it might stop running, right? It might core dump, it might die, the box might die. So Docker run by itself isn't enough to run lots of microservices in a cluster where everyone's talking to everybody. So you need the next level up of awesome, which is Kubernetes. You can't see the bottom. Kubernetes is so hot right now. So Kubernetes is an amazing open source project. I've been in open source for a couple of decades, and for me, Kubernetes is the most amazing open source project I've ever used, consumed, worked with. It's truly, truly amazing. To echo some of the things Professor Dave said in the last talk, Google are kind of the daddies at cloud computing and big data, right? They wrote all the papers on Hadoop, MapReduce, Google File System, Bigtable, Chubby for Zookeeper and so forth. So pretty much the whole Apache Hadoop project is based on Google papers. Google have been running containers in the cloud in their data centers for about a decade. And they kind of have figured out how to do it, right? They kind of know how to scale running lots of containers, running lots of microservices that connect to each other. So they recently published a paper called the Borg paper. If you Google the Google Borg paper, that basically describes Borg, which is their internal implementation of Kubernetes, which is really how they run containers at scale, which is truly amazing. Then what the Google guys did is, I think they finally got fed up of random people from Yahoo writing their papers in Java and Apache, and they thought, we want to actually write our papers ourselves, god damn it, as an open source project. So for the first time ever, Google's actually implemented the Borg paper as an open source project, a public open source project, which is what Kubernetes is. So Kubernetes is Google's latest open source project for how to run containers at scale. It started about 1.5 years ago. And then I work at Red Hat. Red Hat saw it and went, oh my God, this is awesome. So Red Hat jumped in, and we're now one of the major contributors. Koros people jumped all over it. There's people from Microsoft there, and various other companies have all jumped on it. It's got a massive, massive community. But basically Kubernetes it's all written in Golang, and it makes a really small binary. It's really small and simple. And it's basically software to help you orchestrate containers. Now, the term is orchestrate containers, but it always seems a bit kind of wussy to me. Like, oh, I'm just going to slightly rearrange some containers for you. Really what it does is it makes a container as a service platform, or a microservice cloud, right? Don't misunderestimate the orchestrate in there, really. Kubernetes takes Docker containers and turns them into a self-annealing, auto-scaling cloud, right? And rather like the stuff Dave was saying about Google Cloud, what's amazing about Kubernetes is you can just run this on your laptop. You can run this on a bunch of boxes you've got on premise. You can run it in any cloud. You can run it on any infrastructure as a service. You can run it in Google, in Azure, in EC2. You can run it on OpenStack. You can run it on a bunch of boxes that's under your desk or in a corridor. Or if you have a data center of your own, you can run it there. It's really, really awesome. Before I delve into how it works and how you use it and how you can do amazing microservices on top of it, I just want to mention a couple of the other open source projects which are related. There's a project called Project Atomic, which is a Linux distribution. It's from some people at Red Hat. Linux is really traditionally a bit of a monolith, right? If you update libc, all kinds of crazy stuff. That could break anything, right? That's quite scary because almost every app dynamically links to libc. So updating Linux is kind of scary stuff, right? You need a company to pay to help you do that kind of stuff. But what's happening is a less risky way of doing that is saying, well, rather than just having this big monolith where everyone's sharing the same file system, the same shared libraries, let's make a Linux that's actually containers all the way down. So Project Atomic is a new Linux kernel that's rolling into Red Hat Enterprise Linux, which is basically almost everything in the operating system is in a container, which means if you want to update libc, you can do it incrementally on a microservice by microservice basis, right? Start with systemd first if you really want, or whatever. Or start with your one app and update that, and then update something else, then update something else. So it gives you a completely microservice-based operating system, which is kind of cool. Plus Atomic has Kubernetes baked in. So from Red Hat, Kubernetes and Docker are part of the operating system now, right? In OpenStack, we've got Docker and Kubernetes baked in the infrastructure as a service level. And also OpenShift version 3. OpenShift is a platform as a service offering from Red Hat. It's an open source thing. You can run it on premise. You can run it on the cloud. It was always based on Linux containers. In version 3 that came out last year, it's all Docker all the way down or up. But also it's Kubernetes all the way down too. So it's completely based on Kubernetes. So version 3 of OpenShift is a platform as a service, which is basically Kubernetes. So now you've got the option with Kubernetes. Google hosts Kubernetes online on their cloud. There's something called, so Google's cloud is GCE, Google Compute Engine. And then Google's container engine, they thought, damn, we've used the C, what we're going to call it? So they went GKE, as in K for Kubernetes. Get it? So GKE is Google's container engine, which is basically a hosted Kubernetes that you can just run your containers on. So you don't need to worry about VMs and all this kind of crap. Like infrastructure as a service is boring. If you're a developer, just don't even go there. It's just the most boring, tedious, sysadmin-y kind of bullshit, right? What you really want to do is write containers and run those things, because that's fun. That's making apps. That's delivering customer value, right? Stick to the apps and the containers. Don't go to the infrastructure. That's the dark side. That's operations, right? If you're developers, stick to the containers. So if you want to write containers on Google's cloud, Kubernetes on GKE, or you can run OpenShift on Google's cloud or Azure or Amazon, or you can run this on your laptop at home. Okay, so what is Kubernetes? Oh, by the way, here's the OpenShift version of the Docker run. So rather than Docker run, it's OC, just for the OpenShift client. So OC, less typing. OC run, then you give it some kind of name, and then you give it the image name, the Docker image name, and then you do replicas equals 5. Well, it doesn't have to be 5. You give it some number for replicas. Now, this is basically like the previous example for Docker run, but there's a massive difference with this one command. What this one command says is always run 5 instances of this container forever. whatever happens, right? So if any of those processes die, it starts another one. If one of the hosts goes down that was running 2 of those, it starts 2 more on another box, right? This is like a cloud now. This is saying, I always want to run 5 of these things, please. Now I've got something more important to do, and then you get on with your life, right? And so long as there's enough compute power in your cloud, or in your cluster of Kubernetes, Kubernetes just makes that happen, right? Now let me briefly explain how this works. You don't need to really care about this, to be honest. You can just use it. But here's the typical architecture diagram. Kubernetes has a kind of an API server master kind of thing that's highly available. Then it has a bunch of nodes. These nodes have a Docker daemon on them to start and stop Docker containers. And it has a Kubernetes daemon, which we call the kubelet, which runs on every machine. And basically, the master talks to the machines and says, oh, machine 7, you need to run this container now. And it goes, oh, OK. And it runs the container. So it's a really simple model. It's really small and lightweight. If you want to boot up Kubernetes using the OpenShift distribution, it's one binary. You type OpenShift space start. You've got a Kubernetes cluster right there, right? It's small, it's simple. If ever you've tried to run Cloud Foundry, it's between 16 and 36 VMs. I've yet to get the conclusive number, but it's a lot of VMs, right? And it takes a lot of compute resource. Kubernetes is one binary, right? And it's one Docker daemon, one kubelet proxy, and you're good to go. So it's simple, it's small, it's easy, it's not that complicated. Right. Let me talk to you about Kubernetes now as a developer. Let's imagine you want to do some really cool cloud-native apps, and you want to use Kubernetes, and you're not sure if you're going to be on-premise, or you might be on Google, or you might be on EC2, but you just want to write your app once, and you want that app to run on Google, and on Azure, and on EC2, and on your laptop, right? And you don't want to worry about EC2 APIs, and you don't want to worry about infrastructure as a service, because you've got better things to do with your life. So these are the 3 subatomic particles you need to understand to use Kubernetes. Now, probably maybe all these, the meaning of these 3 terms is probably new to you. If you can get your head around these 3 things, you can do awesome stuff on on top of Google's container engine, or on top of Kubernetes on-premise, or on top of OpenShift. The first one is pods, the second one is replication controllers, and the third one is services. So I'll do pods first. Okay, now in Docker we talk about containers, and a container is just a process that's kind of isolated. Kubernetes comes up with this concept called a pod. Now, a pod is a geek joke because the Docker logo is a whale and pod is a group of whales, right? So it's like a joke. A pod means one or more containers, basically. So a pod is one or more containers. The idea behind a pod is the atomic deployment unit that Kubernetes will deploy. So you define a pod and you say, this pod is my one image, and then Kubernetes will either deploy that pod or it will tear it all down again. It never leaves like half a pod around, right? So the pod either deploys or it gets deleted or redeployed, right? You can deploy more than one container in a pod. Now, if you're a Java person, a pod is probably the same as a JVM, right? And that's cool and that's fine. But you can co-locate things. You don't have to, but it can sometimes be useful. For example, you might want to say, oh, I want to co-locate a memcached server with my Tomcat, so that there's always on localhost an in-memory cache, local host away without any network hops. So sometimes you want to have one container, rather like Unix, where you have different containers that do one thing really well. You might have one thing that knows how to grab data from the internet somewhere, and then another is a web server that serves it up. So you might want to put 2 containers together that together make a microservice, but they're really 2 different processes. But don't worry about the co-location thing. If one pod is one container, that's all totally cool. A pod can have environment variables, so you can override environment variables, and you can define ports, you can listen on ports and things like that, and you can use something called persistent volumes, because it might be you want to run a database and you kind of want to keep state in that database usually. So you want to put that state in a persistent volume, which is outside of the Docker image. Docker images usually are just like the installation of the software. If you want to kind of store state, what you tend to do is put that on a different volume, so then the state is independent from the install. So then you can upgrade the software to a new version, and you don't have kind of the state in the image, and it gets all a bit weird. Plus, typically when you run a container, if you're not using persistent volumes and you kill the container, you've just lost your state. So you want to put state, if you want stateful apps, you put that in a separate volume, persistent volume. One other kind of weird thing, a pod has its own unique IP address, which at first seems a bit weird, but if you've ever used Docker on your laptop, you soon get to really love the unique IP address thing. If you run 2 Tomcats on your laptop, it typically either you manually map all the ports in every container, like 8080, and then the debug port, and then the management port, and then the other port. So you can manually go, well, 8080 is now going to be 4080 or something. So you can manually do that mapping. Or you can say, Docker, just give me some numbers. And then Docker will give you some random numbers, and then you have to keep going, oh, it's the second Tomcat, it was 49,300, and what was it, 72? And then we like post-it notes everywhere of what the port numbers are, and it's just horrible. With Kubernetes, every pod gets its own IP address, so all you need to worry about is the IP address, and it's only the last bit of the IP address changes, really. And then you could use port 8080 on all of those pods. So you can say, I'm going to talk port 8080 to all my Tomcats. All you need to worry about is the IP address. We'll come back to that IP address thing. It's a crucial thing. Here's a replication controller. Now, what a replication controller does is it controls the replicas. In other words, it's a terrible name. I raised an issue against Kubernetes. Please call it something else. Replication controller is a really lousy name. But what the replication controller does is it defines a kind of pod you want to run, and then it defines how many you want to run, and then it makes it happen. So it's like a declarative thing where you say, I want to run 3 of these, please. Here's an example of a replication controller. All the resources in Kubernetes are just a blob of JSON or a blob of YAML. You can get and set them over the REST API. You can use a command line tool to get and set them and whatnot, and there's a web console to play with them and stuff. Here's an example. This one's actually running Elasticsearch. You can see near the bottom image, you can see the image is Elasticsearch. That's the Docker image name with a version in it. Right near the top, you can see replicas 1, so that's going to run 1 container at any point in time. If by accident you run another container by accident, it will kill one of them, so there's only 1 running at any point in time. And if you upgrade the replicas to 7, it will run 7 more. So it's really, really simple. Let me just show you an example of that. So here's a little web console. I'm looking at some apps that's running. Here's the replication controllers I'm running. I'm running a bunch of stuff. I'm running some Jenkins. Let me make it a little bit bigger. There we go. I'm running some Jenkins, I'm running some Nexus, I'm running all sorts of bits and bobs. This Fabric8, let me filter on these labels. Let me just look at the console right now. This is the pod which is actually running the web console you're looking at right now. So the web console is a Docker container that's running this web app, which is all static HTML and JavaScript. This is the number of replicas we've said. So if we say, oh, well, let's try 3 replicas, and if the demo gods are working, yay, do you see the number of pods go to 3? So now if we click on the number of pods, we'll see we've now got actually 3 pods. The IP address is just off the side of the screen. There we go. Here's all the unique IP addresses. And we can look inside the logs of either of these. The logs shouldn't be too interesting. All it does is listen on the port. There's not much there. If you really want to get wacky, you can open a console and look inside there's nothing in opt. Let's look in the root directory. That's more interesting. I can't remember where anything is hosted in here. But anyways, you can look inside the container and look inside the file system and all that kind of stuff. What's interesting is there's no SSH daemon or anything running inside the container. Docker has a mechanism for running a command inside a running container, which is almost like you're shelling in, but there's no SSHD or anything like that. You can just execute a command in a container, which is kind of cool. Okay, so that's replication controller. If I go back to the controllers, I can scale down again. I can say, oh, did I say 3? I meant 1, and it will go bang, and it will kill some. Any second now, hopefully. Yeah, we needed 3 anyways. Who needs so few containers? It should update soon. I thought. Okay, any minute now it should go down. Any minute now. Moving swiftly on. So so long as the replicas are bigger than 2, you're good to go, I think. That's what the replication controller does, right? You define a pod. In other words, what's the Docker image? What's the environment variables? Any persistent volumes and stuff like that. You actually use this selector thing. You can give pods labels, key value pairs, to describe the kind of thing you want to run. I'll come on to why those selectors are really useful in a minute when I talk about services. Let's talk about services now. So imagine you're running 5 Tomcats. So that's all kind of cool. We've got 5 Tomcats, and let's say we want to talk to those 5 Tomcats. How do we know what the IP addresses are? Now, we could keep querying the Kubernetes REST API and say, what are all the pods right now, and find the IP addresses of them all, and then we could do our own client-side load balancers. But that's kind of boring. We shouldn't be doing that kind of stuff. That's infrastructure. So Kubernetes has a thing called services, which is a really lousy name because everything's kind of a service, but Kubernetes services are a particular thing in Kubernetes. It's a blob of YAML. If you see API version 1, kind service, that's a service. You define a service, you can give it a name and whatnot. in the specification, in the spec, you give it the port that the service is going to expose itself on, which in this case it's HTTP, so we're going to use port 80, which seems a reasonable thing. The target port is the internal port that we're going to talk to inside the containers, which in this case happens to be 9200. That's just what Elasticsearch happens to use for HTTP, God knows why, but that's just what it does. And then it's got something called a selector. The selector is the key value pairs we're going to query the pods for to find the pods we need to talk to. So one of the things Kubernetes does that Borg never did at Google was it uses labels to help you query pods. Now we can use this for lots of different things, but you can query which pods you wish to talk to for a service. For example, we might want to do an A/B test, and so we might want to run version 1 and version 2 of some software. So we might put the version in a label, but we might, for the service, we might not want to care because we might want to load balance over version 1 and version 2. So you might want to have a service that only uses version 1, and you might want a service that only uses version 2, and then you might want a service that talks to all of them and load balances across them. So using labels, we can kind of query which pods we want to talk to, and we can turn that into a service. So basically, by defining the service and defining the labels, we can define the service, and then we talk to the service, and the service then talks to the pods. What the service actually does, I'll come to that in a second. What the service actually does is it generates a unique IP address for the service for the lifetime of the service. So there's one static IP address that you can use to talk to the service. By talking to the service, what really happens is you talk to something on Kubernetes called a kubeproxy, which every machine runs a kubeproxy. So when you try talking to the service, the kubeproxy kicks in. It uses IP tables to go, you're talking to a service, aren't you? The kubeproxy kicks in, and a local load balancer on your machine where your service, where your container is, then load balances and talks to the actual pods. And that kubeproxy monitors all the pods that match your selector. So as the pods start and stop, it's dynamically changing the list of pods it will talk to. So by talking to the service, you get dynamic load balancing, high availability, and as pods start and stop, the load balancer just automatically just does its thing, which is really, really awesome. One more little detail, Kubernetes lets you define something called a readiness probe that says, starting a container is fine, but if it's like a JVM, it might take, 30 seconds maybe, on a good day, maybe even 2 minutes to start up, right? You have to initialize Hibernate, and you have to load loads of stuff, and you have to wait for the JIT to get going, and all kinds of stuff. So you might want to define a readiness probe that says, until I can query this happy page, where all my message-driven beans are running, all my EJBs are set up, and my web connector is actually serving HTTP, until this happy page returns a 200, don't include me in the load balancer, please. So this readiness probe gives you a trick that you can decide when to include a container in the load balancer. Another common one is you might have a web app that needs to load loads of cached data in memory because otherwise the responses will be too slow. So you might want to warm your cache that on startup you fetch loads and loads of data from a database, load up everything into the JVM. It might take you 10 minutes to be ready, or an hour, whatever. So you can use a readiness probe to tell the load balancer, only include my container when it's really, really warmed up and ready. So then your HTTP responses are fast. So to cut a long story short, services are the way to load balance across pods. It's really simple, really elegant. You just define a bit of metadata, some key value pairs, and you're good to go. A couple of other things about services, though. How many people have used like Spring or dependency injection and Java-y stuff? Okay. So one thing that's kind of slightly wacky. Okay, so think dependency injection in your mind, right? And then imagine a polyglot version of that, right? That works in any language for any service. You can use services as like dependency injection. Okay, let me walk you through it. So a service can be internal, right? I can be talking to a service called cheese, and that could be implemented by pods in my namespace. It could be, though, that the service is in another namespace. It's implemented by another team. And I maybe don't have access to that service because someone else runs it. And they don't trust me to not break their service, so they want to run it somewhere else that I can't see. So you can do something called service linking, where the service I talk to isn't actually in my local namespace. It's actually, we point to where the service is remotely. So you can define, instead of using pod selectors, you can do things called endpoints, where you just describe where the endpoints are where the service is running, which could be outside of Kubernetes. It could be in a different Kubernetes cluster. It could be software as a service. It could be an EC2 service or whatever, and outside of your cluster. Or it could just be inside Kubernetes in a different namespace, like a different logical user space. So you can have services that are internal and external to your system. So there's a new pattern with Kubernetes where if you want to talk to services that your team doesn't make, like imagine databases, right? You might be in a team writing a microservice that needs a Cassandra or a Postgres or God forbid, even an Oracle, right? But your team might not be the people that provision Oracle in the cloud. You might have another team, one team that does Oracle, one team that does Postgres, and one team that does Cassandra, right? So what you might want to do is say, well, I want to talk to a Cassandra. I'll define a service that says Cassandra or Postgres or Oracle or whatever, but you don't specify an implementation. You just make a service with no implementation. Then you call or email or raise a ticket or whatever to the other team that does the database, and they'll wire in an endpoint for you. What's nice about this is you don't have to change your app, which I'll talk about in a second. You write your app once, you talk to your service, and then someone else can plug in an implementation later. So services in Kubernetes are kind of like dependency injection. You define the services for the things you need to talk to, the microservices you depend on, and then over the lifetime of your microservice, you can change where that service is. And you can do service linking and wiring and all sorts of other good stuff. One other kind of thing, services by default are internal. So that IP address for the service is totally internal to the cluster. So only other pods see that service by default, right? These are not global IP addresses by default. You can define external load balancers to get from the outside of the cluster in, like from a web browser or whatever, right? So often your Kubernetes cluster is in a data center somewhere. Usually you can't just get in there with your web browser, so you need to define an external load balancer to get in from the outside. If you define the type load balancer of your service, it's a type in the YAML, then Google's compute engine, Google's container engine, I apologize, Google GKE, Google Container Engine will automatically create a public DNS name and a public IP address and a public load balancer. In OpenShift, unfortunately, that doesn't quite yet work, so you have to type this one command line in, OC expose service foo, and then you get an external load balancer. So both those two ways of how to make services external. Now, one thing I should mention is how service discovery works. So if you're writing a microservice and you need to talk to the foobar service, you give your services the name, whatever you want to call it, foobar. That service is local to your namespace. I should mention this. Kubernetes has a thing called namespaces. Namespaces are a way of taking a bunch of hardware, putting a Kubernetes cluster on it, and then logically splitting that cluster into user spaces, if you like. So if I'm in the James namespace, I could disallow you all from seeing it, right? So I can just have my own namespace with my own stuff running, and you all can't see my stuff. Or more suitable, you might have a production environment that only microservices that are running in production can see other microservices in production, and the test microservices can't see the production microservices. So namespaces gives you a way of kind of sealing an environment so you can't get out by default. So within a namespace, I just talk to foo-bar, and under the covers, the DNS resolution of foo-bar knows the namespace I'm in, and given the namespace I'm in, resolves the service IP address for the service in my namespace. So I can just, in my code, just use http://foo-bar, that's it, no postfix, no dollar squigglies, no environment variables, no like weird stuff. Just, I can actually hard code strings to services now, right? Which is kind of wacky. It feels wrong. As a Java guy, that feels wrong. We should have 4 config files and some dollar squigglies and some profiles that pick which magical dollar squiggly, and the dollar squigglies should all override each other in some really Java-y complicated kind of way. And then JNDI should be a level of indirection to the dollar squiggly. But yeah, you can just hard code things in Kubernetes, which is kind of awesome. And so that works in Node.js, it works in Python, Perl, Ruby, Golang, Swift, and Java, right? You can just hard code everything again, which is kind of cool. So then your one app that's talking to foo-bar, in testing will talk to the testing service, in production will talk to the production service. You don't have to have any magic config files that somebody has to magically edit when it goes from development to testing to production, right? Which is a really, really awesome thing. So services and service discovery is a thing of pure awesome. It takes quite a while for people to really realize how amazing and awesome this is. What's even more amazing, so we talked about Docker and how amazing it is that your Docker image can move from development, testing, production. That's pretty awesome. But what's even more awesome is your Kubernetes manifest can also be immutable and move from development, testing, production. In other words, I can take a YAML file of Kubernetes and a Docker image and run it on my laptop with my Kubernetes install, and I know that that will work on production because it's the same YAML, it's the same Kubernetes metadata, it's the same Kubernetes resources. If I make a mistake in my YAML, it will show up immediately because I'll mistype a service name, I'll mistype an environment variable name, I'll forget to do a secret, or I haven't mentioned secrets yet, I'll come on to that in a minute, or a volume or whatever. In other words, it's pretty clear and quick if anything goes wrong. The only thing that could really mess up, really, as you move from development to test to production, is the thing I'm just about to talk about, secrets and persistent volumes. What's a couple of other resources that Kubernetes does, which you typically don't need to worry too much about as developers writing applications. This is a little bit more operation side. You often need secrets. Secrets are things like login and passwords, SSH keys, GPG keys, tokens for web services, and all those horrible security specs that keep changing all the time, all that kind of rubbish. You need security. You need secrets to be able to access things securely, right? But what you don't want to do is put those secrets in your Docker image so that the production login and password for your production database is then in your development environment that developer can do nasty things with. So what you want to do is take the secrets out of your Kubernetes JSON or YAML and out of your Docker image and put it inside Kubernetes in something called the secret vault. So secrets are a place you put all that secret stuff which are specific to a namespace. Now what that means is in development and testing, you can just do things like, oh, let's just generate like login and passwords for everything, and we'll just automatically populate the secrets for development and testing, because who cares? It's just a test environment. But then in production, your ops people can preload the magic tokens and the magic login and passwords in production, and you can have access control so that only certain people can see those secrets. But at the same time, you can open up production, if you so choose, to let people have read-only access to see what the containers are actually doing. So you can let people see what's actually happening in production, but hide the secrets in a nice, simple way. So secrets are really, really awesome. Environment variables are not a good place to put login and passwords, really, because then you can look at those. You can type env on the shell, and you can kind of find out the password. So yes. Service accounts is a way of adding roles to containers, because sometimes you want different containers that are allowed to do different things. So you can restrict which roles are allowed in different environments through service accounts. You might not need that, but it's just one of those things you might need. Persistent volumes are absolutely key for stateful applications. If you're writing like Tomcat web apps, you're probably stateless and you probably don't care about persistent volumes. If you're provisioning a message broker, or a persistent message broker, or a database, or a stateful service that uses event sourcing or something, you're going to need persistent volumes. The persistent volumes in Kubernetes support pretty much every persistent file system that's of any real decency. All the ones on EBS and S3 from EC2, all of Google's persistent file volumes, all of Azure's persistent file volumes. If you're on-premise using like Red Hat stuff, you've got Cinder from OpenStack, and you've got Gluster and Ceph and NFS, if you really want to go there, and SAN and all sorts of other volume providers. So it's easier to use real persistent engines for your disks, and you just mount them into a volume, and it's really simple. Config map is a new thing. I don't really have time to talk about it, but I definitely don't have time to talk about it. Config map is a way of putting configuration into the environment so that you can change the configuration without having to hack your Kubernetes metadata. 2 minutes, crap. Okay, right, I'm going to go really quick. Here's some command line tools you can use to get and set things, and there's Kubernetes. Okay, Kubernetes is really, really awesome. Continuous delivery. Continuous delivery is the next step, where you want to build your Docker image, you want to take your Kubernetes JSON, and you're going to move it from development to test to production. Now, basically, this is how you do microservices on Kubernetes. You write some code, you put it in a Docker image, you create some Kubernetes manifest, you apply the manifest to an environment, say the test environment, and then you do scaling and rolling upgrades and that kind of stuff. Continuous integration and continuous delivery can automate everything apart from the writing some code, right? We can automate everything else on that slide. The Fabric8 project is a long story. I don't really have time to talk about it too much, but one of the things we've been doing is continuous delivery on top of Kubernetes. Continuous delivery is a bit like continuous integration, but it's more about pipelines and long-running steps. Most people now do continuous integration where you run a bunch of build steps before you commit, or maybe after you've commit. Continuous delivery is more about you run long-term, longer pipelines. Like, I want to run a soak test and a load test and a user acceptance test in parallel. And then with the human approval, if all of that works, I'm going to move it to the staging environment. And then with human approval, I'm then going to move it to production. So it's that kind of automating the flow of software through the environments you need for testing, and then through into production or pre-production. The implementation of continuous delivery in Fabric8 uses something called Jenkins Pipeline, which is a new thing in Jenkins, part of Jenkins 2.0. It was previously called Jenkins Workflow plugin, just to confuse us all, because there's not enough Jenkins plugins in the world. So Jenkins Pipeline is the daddy, right? If ever you're thinking about doing anything CD, look at Jenkins Pipeline. Right now it's called Jenkins Workflow, but Jenkins Pipeline is the official name for it. Basically what happens is you have a Jenkins file in your source code now, and that defines your entire pipeline. So all this stuff about having gazillion build jobs for doing tests and code coverage and the integration tests and system tests and all that kind of stuff, you put all of your flow now in a single Jenkins file, check it into your source control, and Jenkins will now automatically create the builds. Okay, crap, I'm out of time. Jenkins pipelines are awesome. If all you remember from today's talk is check out Kubernetes and try it, it's a thing of pure awesome. And look at the Fabric8 website to see the bits I should have done for the rest of this talk. And use Jenkins pipeline for your CD, of which there's an example. It's a small little Groovy script. Groovy, yeah. It's a small little Groovy script to define your entire flow. And we have an amazing console, which I can't show you just yet, for visualizing your entire continuous integration flow. For example, here's staging and production, and I can see the commits of each one, and I'm waiting for an approval to go to production, and I can test each microservice in each environment. And I can see that they're different. That one returns that, and then that one returns something slightly different because the commits are different. Woohoo! Isn't that amazing? So we have an amazing console if ever you want to try it out on the Fabric8 website. And you can literally watch your approvals. I'm totally out of time. I'm being very naughty. I apologize. So I've just done an approval, and now it's going to it's doing a rolling upgrade. You see, it's going to do a rolling upgrade. It's going to start a new container of the new version, and then the load balancer, when it's green, it's going to kick in, and then it's going to kill the old one. So that's a rolling up. Phew! I got a rolling upgrade in there. Yay! Result. Okay. Thank you. I'm here all day. Cheers. Thank you.